Boston Dynamics just solved one of the least glamorous but most important problems with humanoid robots. What happens when the battery dies in the middle of a shift? The production version of Atlas can now recognize that its battery is running low, walk back to a dedicated battery station, remove the depleted pack, install a fresh one, and go straight back to work. The whole swap takes less than 3 minutes, with no human stepping in. That's a big change for real factory use because battery downtime can wreck the economics of these machines. Atlas gets around 4 hours of runtime during normal operation, but that drops to roughly 2 hours under heavy loads. A normal recharge takes about 90 minutes. So instead of sitting idle for an hour and a half every few hours, Atlas can swap batteries in under 3 minutes and continue through much longer shifts with minimal interruption. And Boston Dynamics is clearly building this version around actual industrial work. Atlas stands about 6 feet 2 inches tall and weighs roughly 198 pounds or 90 kilograms. It can handle sustained loads of up to 66 pounds, around 30 kilograms, and briefly lift as much as 110 pounds or 50 kilograms. Its hands have tactile sensing, and a 360-degree camera system gives it a continuous view of its surroundings. The focus is lifting, moving objects, material handling, and adapting to changing factory environments, rather than following only fixed, pre-programmed routines. It's fully electric, AI-controlled, and the hardware has been simplified in ways that should help both training and maintenance. Atlas uses only 2 actuator types across its body, while its arms and legs have a symmetrical design. Its joints also avoid cables running across them, allowing continuous rotation while reducing wear. That simpler mechanical setup also helps simulation because engineers can model the real machine more accurately. And simulation is becoming a huge part of how Atlas learns. Boston Dynamics has been using reinforcement learning and large-scale simulation to teach heavy object handling, carrying, balancing, and whole-body coordination. The company says modern simulation systems can run the equivalent of millions of hours of robot training in a single day, and learned behaviors can then be transferred to a physical humanoid in roughly an hour. That matters because the sim-to-real gap has always been one of robotics' biggest headaches. A skill can look perfect virtually and then fail on real hardware because of friction, motor limits, timing delays, weight shifts, or tiny differences in the environment. Boston Dynamics says Atlas's simpler hardware architecture helps make the simulation more faithful, which improves the transfer. One test showed how far that has come. Atlas moved a refrigerator weighing more than 100 pounds after training with substantially lighter loads. That requires much more than raw strength. The robot has to see the object, anticipate its weight, control the forces through its hands, maintain balance, and coordinate its entire body while the load shifts. Even the flashy movements still have a practical reason behind them. Kicks, handstands, and backflips force the control system to develop balance, recovery, agility, endurance, and whole body control. Those same abilities are useful when a robot takes a bad step while carrying something heavy or has to recover from an unexpected force. So Atlas is starting to look less like a collection of impressive demos and more like a machine designed around a complete industrial work cycle. Learn quickly, handle heavy objects, monitor its own energy, swap its own battery, and get back to work. Which brings us to how those movements are being taught, because there's a research paper behind them and it's genuinely clever. The RAI Institute, working with Boston Dynamics, built a framework called ZEST, Zero-Shot Embodied Skill Transfer. The pitch is that instead of hand engineering a controller for every new skill, you feed it motion data and it figures out the rest in a single training stage before deployment. It pulls from 3 sources: high-fidelity motion capture, ordinary video shot on a single camera, and keyframe animation. Human movement from the first 2 gets converted into something a robot body can execute through kinematic retargeting, while animation lets you specify motions a human physically can't do, or that make more sense on a non-humanoid frame. And crucially, the demonstrations don't need labels telling the robot when or where to make ground contact. It works that out. The policy itself is trained entirely in simulation and transferred to hardware with 0 fine-tuning. It's a relatively simple feed-forward network that relies only on onboard proprioception once it's running, no external tracking. What it skips is the interesting bit. No state estimators, no long observation histories, no future reference windows, no contact schedules, no elaborate task-specific reward tuning. All the scaffolding that normally makes robot control pipelines a nightmare to maintain. Two mechanisms make it work. The first is adaptive sampling. Rather than training evenly across a motion sequence, Zest chops trajectories into fixed-duration segments and tracks where the robot keeps failing. Hard segments get sampled more often, while a minimum sampling probability keeps the easy stuff from being forgotten. The second is an automatic curriculum built on a virtual assistive wrench applied to the robot's base, essentially an invisible helping hand that's strongest during the hardest dynamic moments and fades out as the policy gets competent. They also did the unglamorous work of building simplified models for the closed-chain parallel linkage actuators in the ankles, knees, and waist, which cuts simulation cost while keeping the dynamics honest. Power limits, motor saturation, transmission losses, friction, all modeled, all in service of that transfer holding up. Results: about 10 hours of training per policy, roughly 7,000 iterations, on a single NVIDIA L4 GPU. That's a shockingly modest compute bill. On Atlas, it produced crawling, forward rolls, cartwheels, army crawls, and breakdancing. From video alone, they got dancing, soccer kicking, and box climbing. And from animation, they had Spot, the quadruped, pull off a continuous backflip and a barrel roll. Same framework, 3 completely different body plans, including Unitree's G1. They're upfront about the limits. It's confined to flat, non-slippery ground, and it hasn't shown it can generalize to motions it's never seen in any form. Next steps they're chasing are zero and few-shot adaptation, continual learning, control via language or keyframes, and generative systems that turn a high-level command straight into executable motion. That last ambition is more or less where NVIDIA's team has planted their flag with a framework called Sonic. Same underlying idea, motion tracking as the foundation for whole body control, but scaled aggressively. One policy, trained on over 100 million motion frames drawn from about 700 hours of motion capture. The largest model runs 42 million parameters. Training consumed as many as 128 GPUs and roughly 21,000 GPU hours. And the payoff was that tracking quality and generalization kept improving as they pushed data, model size, and compute up together. Scaling laws, but for making a robot move. The architectural piece worth understanding is the universal token space. Different input types, robot motion, human motion, hybrid commands, each get their own encoder, and everything gets compressed into a quantized token that feeds a single shared control decoder. That one design decision is what lets the same policy accept VR, teleoperation, video-based control, text prompts, music, and vision language action models without retraining anything underneath. On top of that sits a real-time kinematic motion planner generating short segments between keyframes, continuously replanning as new commands arrive. So you can change direction, speed, or style mid-motion and the robot just absorbs it. Video input works from pre-recorded clips or a live webcam. Text prompts specify things like walking or kicking. Music-driven control pulls rhythm and melody into dance, and the system can hop between modalities on the fly. Deployed on a Unitree G1, Sonic hit a 99.2% success rate across 123 real-world motion sequences against 100% in simulation. So a sim-to-real gap of well under a point, which is remarkable at that scale. They also wired it up to a vision language action model through the token interface and ran 5 whole-body tasks, averaging 75% success. Those tasks included picking objects up, opening a trash can with a foot pedal, and coordinating hand and foot together to drop a soda can in the bin. As the team put it, they expect Sonic to serve as a foundation that higher-level perception and reasoning can be built on top of. Their broader argument is that a shared action representation stops treating locomotion and manipulation as 2 separate problems, which is how most of the field has handled it until now. Meanwhile, on the commercial end, BYD just put a humanoid on its showroom floors. It's called G.O.T. It stands 5.2 feet, 1.61 meters, and weighs 128 pounds, so 58 kilos, 31 degrees of freedom, 7 of which are in the hands. It supports 6 Chinese dialects and 6 foreign languages, and packs facial recognition, gesture recognition, and lip reading. It's launching at BYD's D-Space Experience Centers starting in Zhengzhou, then Shenzhen and Shanghai, with a plan to put 2 or 3 robots in every BYD store. The job description is greeting visitors, explaining vehicle models, demonstrating features, answering questions, pure retail, nothing industrial or domestic. Full showroom deployment is pegged at 1 to 2 years out. The timing isn't accidental. BYD is coming off a 4th consecutive month of declining domestic car sales. June global sales rose 5.5% year-over-year to 403,472 vehicles, but domestic sales fell 22%. First half of the year, they sold 1,808,511 new energy vehicles, down 15.72%, while overseas sales climbed 70.65%. So a company with a massive showroom network and a softening home market suddenly has both a reason to diversify and a ready-made test bed for customer service robots. They've also been pushing their God's Eye intelligent driving platform using AI, cameras, radar, and sensors to cut down on human driving error. XPeng's playing the same game from a different angle, scaling its iron humanoid past 1,000 units a month by the end of 2026, deploying them as showroom sales assistants in China in Q1 2027, then overseas later that year. All of which lands against a policy backdrop that's tightening fast. On July 28, the US FCC added foreign-produced advanced robotic devices, humanoids and quadrupeds both, to its covered list. That blocks new models requiring FCC authorization from being imported, marketed, or sold stateside, though previously authorized devices can keep operating. The stated reasoning is national security and critical infrastructure risk from connected machines carrying cameras, sensors, and network stacks. China's response was to accuse Washington of politicizing trade and technology over what it called unfounded concerns. And Chinese firms are not slowing down regardless. Deep Robotics just released footage of its DR02 humanoid climbing outdoor concrete stairs, real weather, not a padded lab floor. Earlier clips had it running across uneven grass and jumping obstacles, and more recently it's been shown hauling a fire extinguisher mounted on its back while working around high-voltage electrical infrastructure. The DR02 is 175 centimeters, so 5'9", and weighs 143 pounds, 65 kilos with the battery. Arms are 68 centimeters, and it has 31 degrees of freedom split as 6 per leg, 7 per arm, and 3 at the waist, with dexterous hands as an option. Normal walking speed is 1.5 meters per second, about 3.4 miles an hour, with a lab-tested max of 4 meters per second, or 8.9 miles per hour. It'll continuously climb steps up to 25 centimeters and handle 20-degree slopes, with a dual-arm payload of 22 pounds. The headline feature is full-body IP66 dust and water resistance, rated from -4 degrees Fahrenheit to 131 degrees Fahrenheit. Perception runs 1 LiDAR, 3 depth cameras, and a wide-angle camera with an industrial 64-bit octa-core processor, 16 gigabytes of memory, 128 gigabytes of storage, and an AI chip delivering up to 275 tops. Power comes from a 20 amp hours, 1,440 watt-hours swappable pack, and there's modular quick disassembly hardware, so forearms, full arms, and legs can be swapped out fast. The corporate context matters too. The Hangzhou company has applied to raise around $367.4 million through an IPO on Shanghai's Star Market, and the application's been accepted. They posted their first ever net profit in 2025, roughly $4.2 million. Investors are increasingly demanding evidence that these machines move reliably outside scripted demos, which is exactly why the stare footage exists. And their quadruped side of the business has been out-tracking Tibetan antelopes at 4,700 meters, documenting migration and feeding behavior in genuinely punishing high-altitude terrain. That's the week. Plenty more coming. Thanks for watching. See you in the next one.